So let's talk about hydrohalogenation. It's a long word. What it really means is we're going to add HX to a carbon-carbon pi bond. Perfect. Okay, so how does this work? Let's draw a really simple alkene. We'll draw this alkene a lot because it's small and quick to draw, but these reactions aren't limited to this alkene, which is propene. Let's react this with HX, but let's pick a specific HX, like HBr. So what's going to happen is, we know this is a strong acid, and so acids protonate things and they react with things that have electron density. As it turns out, carbon-carbon pi bonds are not super strong, so they're easily broken. So we can break this carbon-carbon pi bond and use that pi bond as a source of electrons to react with our acid. That's exactly what happens. This pi bond breaks, and we're going to use that bond to attack that hydrogen to deprotonate HBr, and we actually have two possibilities. We're not being specific about when this pi bond picks up this hydrogen, where does the hydrogen go? Well, there are two possibilities. We could think of the hydrogen as going over here. I'm not showing all the hydrogens on this carbon, but just that one. If the hydrogen goes over there, that means this carbon has lost a bond. It's going to have a positive charge. And Br minus is going to be our side product. So this is going to form a carbocation. What kind of carbocation? Well, it's going to be a secondary carbocation. Now there's another possibility. The hydrogen instead could have gone on this more highly substituted carbon. And if it did, then that means the carbocation would form instead on the other carbon. And we'd form a different carbocation. We'd form a primary carbocation. Well, what do we know about carbocations? We know that the more stable, the more highly substituted the carbocation, the more stable it is. So this is actually the carbocation that we will form. There are two possible outcomes. We're going to form the more highly substituted carbocation. So this will not be observed. Fantastic. So we form this carbocation. Now we can all agree upon this. What's going to happen to that carbocation? What happens to that carbocation is the same thing that always happens to carbocations. This carbocation will now be either attacked or it will lose a beta hydrogen. So do we have a nucleophile to attack it? Yes, we do. We have Br minus. And that Br minus will come in and attack that carbocation. And so the bromide will end up on the more highly substituted carbon. Why does it go to the more highly substituted carbon? Because that's where the carbocation was that we formed. Now, if this were to react, then the bromide would attack the less highly substituted carbon. And we get this other product. These two products are isomers. And specifically, they're called regioisomers. They both arise from hydrohalogenation, from addition of HBr to the alkene. And we have names for these. When the halide goes on the more highly substituted carbon, because we're going through the secondary carbocation, this is called the Markovnikov product. Now creatively, the other product is called the anti-Markovnikov product. When you do a hydrohalogenation, we will favor the Markovnikov product. And the reason why we favor the Markovnikov product is really driven by the stability of this secondary carbocation. That's the factor that drives forming a Markovnikov product. So when we do addition reactions, and if those addition reactions form a carbocation, we're always going to favor the Markovnikov product. Why? It's because of the stability trend that we observed in carbocation intermediates. So that's a hydrohalogenation. Of course, we could do this on all kinds of molecules. We could react this with HI, and if we went through the mechanism, We'd add HI to that. Of course, we don't have to draw it, but we added HI to that. There's no regiochemistry here because both sides of the double bond are the same. There's symmetry. But this is a hydrohalogenation. We can add HI, we can add HBr, and we can add HCl. No HF. HF does not work for this. It's not acidic enough.